Welcome to a deep dive into logarithmic and modular compensation in Goldbach structures. This model introduces a multiplicative constraint to identify stable prime pairs using quadratic root approximation. We are bridging additive and multiplicative structures. The Goldbach condition is the additive pillar, $p_1 plus p_2 equals $E. By imposing a logarithmic identity, we introduce the multiplicative pillar, transforming the problem into root finding for a specific quadratic equation. Theorem 4 shows the derivation of the quadratic framework. Using the logarithmic identity and additive substitution, we arrive at the quadratic result, $x squared -ex plus EE⁻r equals $0. The prime candidates $p_1 and $p_2 are defined as the roots of this function. Visualizing the roots of compensation, the quadratic formula provides the theoretical ideal values for the prime pair. The actual prime pair will be the nearest prime integers to these real number roots. The calibration problem is finding the constant $r$. While the quadratic equation is valid for any $r$, we must find the optimal value that produces stable roots across all tested magnitudes of $e$. We test $r equals $1, $r equals $e$, and $r equals pi$. Trials with unity, $r equals $1, resulted in instability as solutions crowded narrowly around 3. The trial with Euler's number, $r approx. $2.718, led to the Euler trap, frequently yielding composite semiprimes as outputs. The discovery shows stability at $r equals pi$. For $e$ up to $10, carat $12 $r approx. $3.141593 results in a stable solution where $p_2 equals $23. This fixed anchor prime forms a robust compensation structure. Theorem 5. The logarithmic anchor theorem states that for large even integer $e$, the prime pair $e2323 serves as a stable, log-compensated solution. $pi$ represents the optimal offset constant, and $var_e$ is the error term. Asymptotic verification of the error term shows that $var_e$ converges to approximately -$0.0061 as $e$ approaches infinity. This provides a robust, predictable deviation from a perfect logarithmic balance. Theorem 6 explains how to move from real roots to prime integers. Since the roots of the quadratic are floating point numbers, we use a nearest prime substitution to minimize the logarithmic deviation, $delta caret text prime underscore log $. Interpreting the integral deviation, the antiderivative of $f of x equals x squared -ex plus EE⁻ pi$ represents the cumulative deviation. The extrema of this function correspond to points of minimal mismatch between the multiplicative and additive constraints. Implications include multiplicative duality and connections to the Riemann zeta function. The prime distribution around the quadratic centers may illuminate aspects of the distribution of non-trivial zeros of $z is $. In summary, logarithmic compensation provides a multiplicative check on Goldbach's problem. $pi$ is the optimal constant, and the pair $e2323 is the asymptotically stable solution with a vanishing error term.